Okay, let me start the session. If anyone joins late, I will let them in. So let's start. Okay, is the screen visible?
Yes, sir. Screen is visible.
Okay, thank you. Thank you. Good evening, everyone. Myself, Arka Roy. I'm working as a Prime Minister's Research Fellow in the Department of Electrical Engineering, IIT Patna. And I will be your PMRF TA for this course on discrete time signal processing. This course is offered by Professor Mrityunjay Chakravarti, IIT Kharagpur, and this is the week 2 live session for this course. So let me just move to the content of today's session. So this is the brief content of today's session. So we'll start by recapping the content that is basically covered in week 2 by Professor Chakravarti. And after that, we'll start solving some numerical questions based on the topics basically covered in week 2. Basically, in week 2, the main theme is DTFT, that is discrete time Fourier transform. And then after solving the question, we'll have a Q&A session regarding if you have any queries about the quizzes and other things. So let me tell you, week 1 and week 0 and as well as week 2, all these quizzes are live currently in the course website. And due date of week 1 quiz is, I guess, it's 9th of August. So as because this is just 4th of August today, so I will not be able to make any remark. I guess someone is trying to join. Yeah, let me just. Okay. So what I was telling is that week 1, week 0 and week 2, all these quizzes are live in the course website, and due date of week 1 quiz is on 9th August. So as because it's 4th August only, so I will not be able to make any remark on week 1 quiz, and I will not be able to discuss any questions that is basically there in week 1, as because you have not been graded yet. So after grading is done for week 1 quiz, then we can have a discussion on week 1 quiz questions. If you have any query regarding the how the solution has been done and all, so we can talk about that after 9th August. And feel free to interrupt me at any point of time. If you have any questions, just ask question. That's not a problem. So let's just move to the content. So we'll start with the basics of a discrete Fourier transform. So till now, what is basically covered is that what is discrete time system, what is digital system, and some basic operations on discrete signals, and what is the linear system, time invariant system, LTI system in general, and what is convolution, stability, and these things. So we have seen that if there is a system T, and if you give any input, let's say discrete input, okay. So if there is a system T and the input is Xn and output is Yn, then Yn we can write it as let's say it has an impulse response or unit sample response is Hn. So we can write Hn convolved with Xn, and similarly we can write it like this, Xn convolved with Hn. Both basically means the same thing. Now, if I expand this, I can write it like this, Hr x of n minus r, where r is running from minus infinite to infinite. Now let us consider the input signal. Input signal is xn is equals to a to the power n. So for this particular signal, what will be the output of the system? So we can start it like this, h of r, a to the power n minus r, as because we are dealing with n minus r argument, and this is basically running on r. Then we can take out the a to the power n part, and we can write it like this, h of r, a to the power minus r equals to minus infinity to infinity. So we can see that we had inputted a to the power n as the input sequence of the system, and we are getting something like lambda into a to the power n as output. That means this is basically called an eigenvalue, and this is called an eigenvector. But as because we are dealing with sequences in this particular course, in matrix, in basic engineering mathematics, we call it as an eigenvector. However, as this is basically a discrete signal processing course, so we'll call it as an eigensequence. Therefore, the lambda looks like h of r, a to the power minus r, where r is running from minus infinity to infinity. Now let's say a to the power n, if it was inputted as like uh, e to the power j omega, uh, e to the power j omega n, that means effectively if a is equals to e to the power j omega, then what would be the response? So response would be equals to, let's say I can change the variable name at any point of time. That will not hamper the output of the summation. So I can write it like this, a to the power minus n. So I can treat it like this, e to the power minus j omega n. N is running from minus infinity to infinity. So this particular operation is basically referred as the DTFT of any discrete signal. So DTFT, and we denote it as DTFT is denoted as h e power j omega. The argument is j omega, whereas in continuous Fourier transform, we basically see it like this, h of j omega. So instead of that, this was a CTFT thing, continuous Fourier transform. We write it like this. However, as because this is a discrete time Fourier transform, the notation basically changes a little bit, and h of e j omega, and we can write it as h of r. Sorry, h of n. It would be h of n, then e to the power minus j omega n, and n is basically running from minus infinite to infinite. So this thing is basically called the DTFT of any sequence. So with this, we'll be moving forward to the next topic. So this is very intuitive building block of any discrete signal processing course, because very often we'll be transforming the time domain signal into frequency domain signal. So for that context, DTFT plays a very vital role, because it helps in filter designing, frequency domain operations like that. Now we have seen that if we are basically given the xn, we can get the x of e power j omega, that is the DTFT. Okay. Now let me write it like this. Shouldn't put, yeah. So given the time domain, sorry, given the discrete domain signal x of n, we get the DTFT. Now the question is that, is the transformation is reversible? That means if we have x e power j omega, can we get back the uh, sample domain or discrete domain sequence? So how to get that? So let's start with the derivation. X e power j omega. We all know that it is basically n equals to minus infinite to infinite xn e to the power minus j omega n. Now, there is a very beautiful property. We know that the DTFT, it basically repeats in between minus pi to pi. That means it's a periodic sequence in 2 pi. Therefore, I can take an integration of minus pi to pi x e power j omega. Then let me just multiply with the factor e to the power j omega n, and I can write it like this: x of r e to the power minus j omega r. Let me just change the variable, and I will be taking integration in the both sides. So minus pi to pi, and then I will be multiplying with the same factor e to the power j omega n, and then obviously d omega, both sides. Now, if I solve the integral for this particular side, minus pi to pi, so when summation and integration are basically there hand by hand, so we can just interchange the position of these two. So r from minus infinite to infinite, x are basically depends on r, so I will take it out from the integral, and then minus pi to pi e to the power minus j omega r minus n, and then d omega. Now, what we are doing, we are taking some particular r, then with that particular r we are evaluating the integration, and then we are adding with the next term, or based on the next r we are doing the same computation and adding all these values. So let me fix r for this particular case. So we can write it like this: when r is equals to n, that time xn minus pi to pi e to the power minus j omega. So r is equals to n, that means e to the power j omega 0 d omega, followed by that. So r equals to minus infinite to infinite. Only the other condition is that r not equal to n, because for that particular condition we already have derived the summation part, and then it will be just as it is. So x of r minus pi to pi, then e to the power minus j omega r minus n d omega. That's the same thing. Now we can write it as x of n into this will be evaluated as minus pi to pi, and this will be 1. So d omega. So this is 2 pi. So the evaluation of this thing is 2 pi. So I can directly multiply with 2 pi. Now the catchy thing is, let me just change the color. So the catchy thing is this part. So what is the integral value of this particular thing? So what we are effectively doing, e to the power minus j omega r minus n minus pi to pi d omega. So e to the power I theta, we know it is basically cos theta plus j sin theta. And within a period, let me show you, within a period, let's say this is sine. So 0 to 2 pi. So it has a period of 2 pi, that means minus pi to pi also. The uh, relation will be like this. Okay, uh, this minus pi, this pi. Okay. So if we integrate this sine over 0 to 2 pi or minus pi to pi, then the integral value will be 0. Same basically it holds for cos also. Therefore, the whole integration of this thing, it will effectively reduced to 0. That means whatever integration is basically evaluated over here, that will lead to 0, and 0 multiplied by this whole thing will result in 0. So in this side, it is minus pi to pi x e power j omega e to the power j omega n, and then we can write xn as 1 upon 2 pi. I'm just transforming it over here. So minus pi to pi x e power j omega e to the power j omega n, and obviously there is a d omega. So in this way, we can get the discrete domain sequence again given the DTFT of the signal. Okay. Now we have the cascaded system. So cascaded system means, let's say we have two systems, H1 and H2. Let me just make them small letter. So this is H1n and this is H2n, and these two are fade like back to back. And this is the output yn, and this is the input xn. Now, given this system, what will be the output of the system? So this is H1n convolve with H2n convolve with xn. So this is the output. Now, if I tell you that what is the effective system response. So let's say the effective system response is HN, and okay, I guess someone is trying to join. Okay. So this is XN, and given this XN, we have this system, and we need to find what is the effective unit sample response of this particular system. So we can write HN, that is the effective sample response, H1n convolve with H2n. Now, if the DTFT of H1n is H e power H1 e power j omega and H2n is H2 e power j omega, then we know that if there is a convolution in the discrete sample domain, so if we take Fourier transform in both the sides, so Fourier transform H1n convolve with H2n. So in the time domain, there is convolution. So if we take the frequency domain response, then it will be just the multiplication. So h e power j omega, it will be h1 e power j omega multiplied with h2 e power j omega. That means time domain, or let me be very specific, sample domain. If time domain or sample domain, there is multiplication. In the frequency domain, it will be convolution, and vice versa is true. That means if there is convolution in the time domain, frequency domain, it will be reduced to just multiplication. So this is how basically the cascaded system looks like, and it is basically very helpful when we start designing the filters. So if we have 2 or 3 filters back to back, so then we don't have to do convolution each of the time. We just need to convert the signal into frequency domain, and then the filter parameters are also basically provided in the frequency domain, and we'll get the response of each of the filter. And we just have to multiply all these filter responses to get the output sequence. So this way, we can deal with the cascaded discrete time systems. Okay. So next thing comes that what is the relationship between a CTFT and DTFT? CTFT stands for continuous time Fourier transform, and we need to find what is the relation between these two systems particularly. So let me just. So this is a signal, continuous time signal XAT. That's why I'm telling it as an abbreviating it as analog signal. And so this is the envelope. Okay, again, I guess someone is trying to join. Yeah. So this one is the analog signal or the continuous time signal. And this one, let's say Xn, that is the discrete sequence. So we'll be having some samples. So I just have drawn the envelope so that it looks kind of same. Otherwise, the drawing will be pretty messed up. So this is T and this is K. Now, how can we get the what you call the sampled sequence from the given analog sequence? So in the last week, I have shown you that how to get a discrete sequence from given analog or continuous time signal. What we have to do is just let me change the color. We just have to multiply with Dirac delta form signal. So this is basically a delta signal. Delta, we can write it as t minus mt. Still, it is in time domain. So with this time domain signal, when we multiply this signal with the analog signal, we'll get the discrete time sequence. Now we can write that XAT is basically multiplication of xn. Xn is basically multiplication of XAT, and let me name it as ST. So if we multiply these two and then we'll get the sequence signal instead of the time domain signal. So this will be transformed when we'll do the dot multiplication. Now we can take an analog Fourier transform in this way, minus infinite to infinite. So XAT ST and okay, let me just take two of this. So XAT ST e to the power minus j sigma t dt. So this sigma that I have written over here, this sigma is analog domain frequency. So sigma has a radian per second. So that means radian divided by time. Now this is the unit of sigma. Now let me we can write ST as because this is a periodic sequence. We can represent any periodic sequence in terms of their Fourier series decomposition. So if we write the Fourier series decomposition Cn, then e to the power j sigma naught. Now sigma naught is basically the fundamental time period. Now the j sigma naught n and then t, and n is running from minus infinite to infinite. So how can we get the Cn? So Cn is basically 1 upon t with a period of t, then st e to the power minus j sigma naught n t dt. Okay, now 1 upon t. So the period, so this is 0, this is t, this is 2t. So likewise, I can consider this one as a period from minus t by 2 to t by 2. So minus t by 2 to t by 2. And st within that period is basically just delta t and e to the power minus j sigma naught mt dt. Now, if delta Dirac is multiplied with any particular sequence or any particular signal, so we can write it like this: that signal evaluated at that particular instant of time when delta t exists. Now, as delta t I have written, it is existing at t is equals to 0. So I can put t equal to 0 over here. So delta t into e to the power minus j sigma naught n multiplied with 0, then dt. So 1 upon t. So the limit is minus t by 2 to t by 2 delta t into 1 into dt. And within these particular region, the integration value will be 1. So 1 upon t into 1. So 1 by t. That means st, I can write it like that: 1 upon t cn e to the power, oh sorry, cn is 1 upon t. So I can write it like this: e to the power uh, j sigma naught n t. Okay, fine. Now minus infinite to infinite xat, I can just replace it over here with 1 upon t e to the power j sigma naught nt, then multiplied with minus j sigma t dt. Separation over here. Okay. So 1 upon t, I can interchange the uh, integral and summation signs. So minus infinite to infinite, and this is n equals to minus infinite to infinite. So minus infinite to infinite over here. Then 1 upon t I have taken outside of the system. Now the integral basically depends on xat, and I can write it like e to the power minus j sigma minus sigma naught n t dt. Fine. So this particular thing, I can refer it as sigma dash. That means we are evaluating this particular integral at sigma dash uh, uh, analog frequency. So for that particular application, we can write it as n equals to minus infinite to infinite. And this is what? This is the analog Fourier transform or the continuous Fourier transform evaluated at sigma naught n. So that means this is basically the relationship between x e power j omega. So this is the digital sequence or discrete sequence. This has a DTFT of x e power j omega, and this is basically related with the continuous time Fourier transform like this j. So I guess this, let's see. So let me just write it over here. So if xn is basically xat st and xn has a dtft x e power j omega, and this part, if this is, I take ctft over here and this is dtft over here. So the ctft will become 1 upon t summation x of just see, yeah, x x j. This will be sigma minus n sigma naught. Fine. So now we have equated these two things with each other. Therefore, if we take their transforms, so transforms will also be equated. So x e power j omega will be equal to 1 upon t n equals to minus infinite to infinite x j sigma minus n sigma naught. So this is the relationship between the discrete time Fourier transform DTFT, and this is basically the CTFT part. So in this way, DTFT and CTFT, these two are related. So if we have the discrete sequence, we can evaluate its what we call the continuous time Fourier transform. And even if we have the continuous time Fourier transform or the magnitude spectrum of the continuous domain signal, we can get the DTFT as well. So this part is same for the DTFT and CTFT. So we can omit this one as already we have discussed. Now the final topic is that Professor Chakravarti has covered is how to get back a continuous time signal from the DTFT. So DTFT, as it is mentioned, DTFT looks something. Let us consider DTFT is looking like this. So DTFT is periodic in between minus pi to pi. So let me write it as minus pi to pi. And the band limiting frequencies are omega h and minus omega h. And this is x e power j omega. Now we are given this particular thing. So we are just given the DTFT of a sequence. And now from the DTFT of the sequence, can we, let me just give this particular notation. So one-sided array. So from the DTFT, can we get the x of t? So this is the question. So we know x e power j omega is equals to summation x of n e to the power minus j omega n. N is running from minus infinite to infinite. And uh, this particular axis is omega. And this is a period sequence with respect to digital frequency omega. So digital frequency omega has just the unit of radian. Okay, now we can move forward with the question. So to get the envelope, to get the real continuous domain signal, we have to get the from the DTFT, we have to get the CTFT first. If we get the CTFT, we can take inverse Fourier transform, inverse continuous Fourier transform to get the time domain signal. So for that, the process is in step one, we'll take out one particular period of the DTFT. So omega h, and this is plus pi, and this is minus pi. Then previously we have seen that in this particular slide that given the DTFT, how CTFT is related. So the CTFT relation is 1 upon t. That means the amplitude is basically damped by the factor of t. Now to get the CTFT, we need to multiply this t back with this particular DTFT sequence. That means we'll be multiplying this thing over here. So t into, let us consider previously it was 1. So t now, as because we have multiplied with this particular thing, so omega minus omega h, and this is pi, and this is minus pi. So the first step is t into x e power j omega. So this we have to evaluate. Then that means we have found out the CTFT relation. Now just we have to take the inverse Fourier transform in the continuous domain. So xat, I can write it like this: 1 upon 2 pi minus infinite to infinite, as because we are doing the continuous time Fourier transform, inverse Fourier transform. So the integral limit is from minus infinite to infinite, and then xa j omega. That means this is continuous time Fourier transform multiplied with e to the power j sigma t dt. So we can expand it like this further. So just to get the flavor of the DTFT. So I can write sigma s by 2, sigma s by 2, then t into x e power j sigma t and e to the power j omega t dt. And this way, if I now just put another relation, sigma is divided by 2, sigma is divided by 2, t into, now I can take the DTFT definition, xn e to the power minus j omega n, and n is running from minus infinite to infinite, e to the power j sigma t dt. Now, after we get this whole integration and summation part, uh, in the course slide also, you have seen that professor has already solved this particular integral, and the final result basically is called the Nyquist interpolation equation. So I'm not solving the whole equation. So let me just refer to the final answer. So it will look like summation x of m, there will be a sinc function and it will be related as pi by t and then t minus nt, sorry, it's xn, and n is running from minus infinite to infinite. So in this way, we can get the time domain sequence given the discrete Fourier transform of a particular sequence xn. So we can get the xn by doing the DTFT and IDTFT, and then we can just multiply with the sinc factor, and we can add all the particular instant from starting from minus infinite to infinite, that is basically the n index, and we can get the final analog signal. So given the DTFT, we can get the analog signal. This is XA. So this way we have tried to cover the recapitulation part for this particular week, and uh, we'll start solving some numerical questions that I have noted down that will be helpful to solve this particular week two's live questions that are there in the course website. So let me start with the problem. So the problem basically states that we have a sequence xn and the sequence. Oh, okay. I guess someone is trying to join. Okay. Mm. So this is xn. So the sequence is given as like this, and x0 is given as 1. That means the sequence is basically starting from here. So this is n equals to 0 point. And we have to find the value x e power j omega. So we can start solving like this. X e power j omega, we know it as x of n e to the power minus j omega n. N is running from minus infinite to infinite. Now in the question, they have particularly asked to find x e power j omega. That means it will be omega evaluated at pi. So I can further write it like this: x of n e to the power minus j pi n. And further I can write it like minus infinite to infinite. And even I can decompose it like this: x of n multiplied with cos pi n minus sine j sine pi n, minus infinite to infinite. Okay. Now we just have to put the values and get the answer. So xn is basically given as 1, 2, 3, 0, minus 3, minus 2, minus 1. And this is the starting point. So we can start evaluating x e power j pi is. Now let me just tell you some trigonometric relations that we all know. Just this is a recap again. So cos pi n and sin n pi. Let me write it like this: n pi. Sin n pi is 0 for any n pi, or let me say for any n particularly. It doesn't matter whether n is even or odd. However, cos n pi, it is varying from -1 or 1. So -1 when n is equals to odd, and n when 1 when n is equals to even. If we just plot the graphs of these two, so sine is pi 2 pi, so we can see that at pi and 2 pi at both the positions this is 0. However, cos, it will start from 0 like this and this. So this is 0, this is pi upon 2, this is pi, and this is 2 pi. So we can see at pi this is -1, at 2 pi this is +1. Therefore, for any odd values of n we can get -1, and for any even values of n we can get 1. So let me just put the values over here. So xn is 1, and if we put 0 over here, so this is multiplied with 1 minus 0. Okay. Then second sequence, I will take 2. Now n is equals to 1 at that position. So cos pi is equals to -1 and sine is 0. So we don't have to bother about sine, because for all particular case, this is basically reduced to 0. Okay. So this will reduce to 0. So I will just have to bother about the cos part. Now 3 multiplied with cos 2 pi. So that means it will be 1, then 0, then -3 multiplied with now 0, 0, 1, 2, 3, 4. So again n equals to even, that means 1, then -2. So n is odd, so -1, and then -1. Now n is 6. At this position n is equals to 6. That means it is what you call n is even. So if we evaluate this thing, so it will be 1 -2 +3 -3 -2 -1. So minus plus over here. Okay. So 3 cancels each other, 2 cancels each other, and 1 is also cancelling each other. So the output is 0. That means x evaluated at DTFT evaluated at omega equals to pi, the output is 0. So the answer of the first question is 0. Moving forward to the second question. So x of n is equals to half to the power n un. So can you tell me that whether this particular sequence xn, whether it is a right sided sequence or it's a left sided sequence? You can answer the question whether the sequence is basically xn is basically right sided sequence or left sided sequence.
Right-sided
Anyone?
sequence.
Okay, yes. As because we are multiplying with un, that means it will obviously be a right sided sequence. So the question is that this is xn given, and yn is related with xn like just a squared relation. Now we have to find the Fourier transform of yn, basically the DTFT, and that will be evaluated at omega equals to 0. That means y e power j omega, okay, y e power j omega is equals to yn e to the power minus j omega n n is equals to minus infinite to infinite. Now in the question they have given that omega equals to 0. We have to evaluate at that particular point. So y e power j0 will be equals to how much? Yn minus infinite to infinite. As because this particular thing will reduced to 1. Now just we need to take the summation of that particular sequence yn. So that is the main thing. So how yn looks like, let me just draw the sequence for you. So it will start from n equals to 0. I am drawing y of n. Okay, let me start with xn. Then it will be more appropriate. At n equals to 0, this will be just uh, half to the power 0, 1. Then at n equals to 1, this will be 1 by 2. At n equals to 2, this will be 1 by 4. At n equals to 3, this will be 1 upon 8, likewise. Now yn is xn whole square. That means the sequence will look like this. So this will be 1 at n equals to 0. Then at n equals to 1, this will be 1 upon 4. This will be 1 upon 16. This will be 1 upon 64. Pardon my drawing because the values are, this should be little more down, but still it's okay. Now the sequence of yn, we can see that this is 1, then 1 upon 4, 1 upon 16, 1 upon 64, like that. And this is the starting point. So we just have seen that y e power j0 is summation of yn, n running from minus infinite to infinite. And let me just copy this part over here. Okay, yes. So this is the sequence that looks like yn. So the summation will be 1, 1 upon 4, 1 upon 16, 1 upon 64. And till infinite. So we can see this is a infinite GP series with the common ratio of 1 upon 4, which is less than 1. Therefore, if a GP series is there and the summation result basically is A divided by 1 minus R. R is the common ratio. Infinite GP series sum is basically referred as A by 1 minus R. A is the first term and R is the common ratio. Therefore, the first term is 1. Common ratio we have already derived, that is 1 upon 4. So 1 minus 1 upon 4. So this will be 4 by 3. Final result is 4 by 3. Therefore, y e power j0 will be effectively reduced to 4 by 3. Okay. So any questions so far regarding the questions? Regarding the problems that we are solving? If you have any questions, you can ask. Or I will move forward with the next question. Okay, it seems there is no question, so let me move forward with the next question. So the next question is the autocorrelation sequence of a signal xn is defined like this. So we have given a particular sequence Rn, which is basically comprised with this particular formation. x star k and multiplied with x n plus k, and the summation is running on k minus infinite to infinite. Now the question is that we need to find the DTFT of this particular sequence. So I can write Rxn is equals to k equals to minus infinite to infinite x star k x n plus k. So in DSP questions, let me tell you, in DSP questions, so all the questions are basically linked to the very root of the DSP concepts. So you have to be very careful about the all the previous relationships as well that we have covered so far. For example, um so this particular equation, if I just manipulate this particular thing, so can you just tell me, let me just first show you how I am manipulating the equation. So let me take k equals to minus m. Let k equals to minus m. So when k goes to minus infinite, m will go to infinity. And when k is infinity, m is minus infinity. So I can write it m is equals to plus infinity to minus infinity x star, and I can write k as minus m and x of uh, n minus of m like this, and I can write the summation as, because let us consider we have a particular signal. This is the signal, and this is spreaded from minus infinite to plus infinite. This is 0. So integrating the signal from minus infinite to plus infinite, integrating the whole signal from this range to this range, from this direction to this direction, it will, let's say, yield a. Total integral value is, let's say, a. Now, if I integrate the same thing from right side to left side, so this will effectively the area under the curve. So if I integrate the whole thing from this side to this side, or from this side to this side, this will effectively reduce to same value. That means summation, if I can exchange the limit from minus infinite to infinite, x star of minus m, x of n minus m. Okay, so this is basically the final version after taking k equals to minus m. Therefore, can you tell me that this relationship looks like a very known relation that we have covered in week 1. So uh, what is this particular relation? Anybody? So in week 1, we have talked about the convolutional systems. So convolutional systems. So let me just write it like this: xn h of n. So we were writing it like this. Let's say hn and x of n minus. Uh, this is r. This is r. H of x of n minus r, and the summation was running on r from minus infinite to infinite. Likewise, if I see these two particular things, so we can get some idea about it. So this is just the convolution operation in between x star minus m. Let me just write in n, because your effective output will be in n only. So x star minus n convolution with x of n. That means Rx of n is reduced to x star minus n convolve with x of n. So this is the first level of solution, that we have reduced this particular thing to this one. Now let me just copy this part to the next page. Okay. Now what we have asked to find the DTFT of Rxn. So DTFT of Rxn, let me write it like this: Rx e power j omega will be DTFT of this convolution thing. And just previously, while recapping the content of week 2, we had seen that if there is convolution in the time domain or in the sample domain, so in the frequency domain, that will be reduced to multiplication. Therefore, we can write it as DTFT of x star minus n multiplied with DTFT of x of n. Fine. Now for x of n, we all know the DTFT is simple x e power j omega. Now the question is, what is the DTFT of this particular thing? So we need to evaluate the DTFT of x star of minus n. So let me try to find the DTFT of this particular sequence. So summation x star minus n e to the power minus j omega n, and n is varying from minus infinite to infinite. So I can take this conjugate or this star out of the system. How? So I can write x of minus n e to the power j omega n, and then we can take the star over here. So if I take the star inside, so it will be just x star minus n, and this will be complex conjugated. So there will be a minus sign over here. So n equals to minus infinite to infinite, and this is fine. Now I can change the variable. Let minus n equals to m. So again the same thing, m is equals to plus infinite to minus infinite, which I can interchange obviously, because integrating or summation or taking sum of the whole sequence from left to right or right to left, this will effectively reduce to the same output. Therefore, uh, I can write it like x of minus x of m e to the power minus j omega m. That means, and obviously there is a star. That means this is effectively reduced to x e power j omega. That means this whole thing is inside this thing is what? X e power j omega and x e power j omega, and we are taking the conjugate of this. So effectively x star e to the power j omega. That means x star minus n has a DTFT of x star e power j omega. This is a very important relation for as far as problems are being concerned. So in many problems, you'll be given these kind of sequences, and uh, you will be told that how to you will be told to find the corresponding DTFT. So this is the DTFT thing. Now we are left with the final part of the question. So let me just change the color over here, and Rx e power j omega. We just need to multiply the DTFTs. So first one DTFT is how much? X star e power j omega and x e power j omega. That means it will be and there is a multiplication. We know from basic complex theory mod z, we can write it as z multiplied with z star mod z square. So we can write the same thing like uh, x e power j omega squared. So Rx e power j omega is mod squared of the original sequence DTFT. So as far as question is being concerned, the final answer is this, but uh, we can draw some conclusions from here. So if a sequence is given, so the sequence is, let's say, Rx of n, and we have found the DTFT of Rx n, and which is reduced to this particular thing. So
Sir, I
yes,
have a doubt.
yeah,
Sir, in the left side you have written z conjugate z multiplied by z conjugate is equal to mod z square, na?
yes, yes, yes.
Okay, then fine, sir.
Uh, okay. So what I was telling is that if you have given any sequence, let's say this is Rx of n, and you have been told to find the DTFT of that particular sequence. So we have found out the sequences like this. So we know that Z is composed of A plus JB and Z star is A minus JB. So Z mod Z will be just the magnitude part. It will have magnitude only. There will be no phase. Am I right? So for Z mod Z square, there will be no phase present in the output. That means this particular thing has zero phase. Only magnitude is present. And uh, if you have studied the any signal system course or any basic continuous time signal processing course, so there you must have seen that if the time domain signal is real, then its Fourier transform is contains only the magnitude part. That means only real. It doesn't contain any complex forms. That means it has zero phase. So this is a very important relation. If your given sequence is real, so your your DTFT will only contain of magnitude. There will be no phase. That means a zero phase system. So zero phase system you will see in probably week 3 or week 4 while designing the filters. So in MATLAB, there is a command called, you can check these things in MATLAB. There is a command filt. FILT. So this command basically performs zero zero phase filtering. So you can check these things in MATLAB also. So field basically gives you the zero phase filtering concept. So moving forward to the next question. So we have been told that if x e power j omega is the discrete Fourier transform of a signal xn, then we need to find the inverse DTFT of x e power j omega. So I will solve it in two manners. So method 1 and method 2. So method 1 could be a bit confusing. So I will suggest you to, if this kind of question comes, solve it using method 2. So as far as the problem is concerned, so the xn has a DTFT of x e power j omega, And we know x e power j omega, we can expand it like this, x n e power minus j omega n. Now we have taken a conjugate sign over here. So x star e power j omega, and then x of n e to the power minus j omega n, and there is a conjugate sign over here. I can take the conjugate sign inside this also. So that means x star n e to the power j omega n, and n is running from minus infinite to infinite. Fine. Now I can change the variable. Let n is equals to minus m. So the same thing happens. The limit will be changed and it will have the limits plus infinity to minus infinity. And we already have told twice that we can interchange the limits, as because summing from this side to this side are same. So x star minus m e to the power minus j omega m. So we can see from the relationship that this is particularly the uh, what you call the sequence is now the input sequence. Initially, if we were given x of n, so we can write the DTFT like this. Now the input sequence itself is basically x star of minus n. So we can write it as DTFT of x star minus m. Now I can uh, give you the relation is like DTFT of x star e power j omega is basically DTFT of x star of minus m. So even I can change the variable also, x star of minus n. That means x star e power j omega will effectively reduce to the DTFT of this particular sequence, and which is there in option C. So we have got the relationship that how if a given sequence xn is given and we have been told some transformation is applied on the DTFT itself, we can get the relationship with the corresponding time domain variation. So this is the method one solution. Another thing we can do some when you'll be solving the questions. So, and if you get a hand on the particular thing, so you can start with some probable guess like x star of minus n. If I take the DTFT of this, let me take the DTFT of this particular sequence. So I can write it like x star minus n e to the power minus j omega n equals to minus infinite to infinite. Okay. Now I can change the variable again. So it will effectively reduce to x m equals to infinite to minus infinite x star. So minus m will be replaced by what? M, and e to the power j omega m. Then I can take this star out again, e to the power minus j omega m, and I can take this star out, and now this is running on m, and even I can write it like this, x of m e to the power minus j omega m. I can take the whole star out of the system, and then I can write it like this. Inside this is what? X e power j omega, and then from the outside we are taking the star. So x star of e power j omega. That means x star of minus m is basically having the corresponding DTFT x star of e power j omega. So with this, we can get the solution that given the signal xn, if we do some transformation on the DTFT, we can get the corresponding time domain sequence relationship, that how this is basically transforming the time domain signal as well. So this is the particular solution. So moving forward with the next question. Okay, so we need, there is a sequence xn and we have been told to find the DTFT. So xn is this is alpha to the power n un. Again, this is a right-sided sequence as because we are multiplying this with un, and given that alpha is less than 1. Okay. Now we need to find x e power j omega. So x e power j omega will be summation xn e to the power minus j omega n, and n is running from minus infinite to infinite. That's why I'm not writing this thing again. So I will just abbreviate as summation over n. Now it is alpha n un e to the power minus j omega n. Now till this point, let me just write it over here. Till this point, n is running from minus infinite to infinite. Now as we proceed to solve this particular summation, as we know that un only exists for, so un's definition is 1 from n greater equals to 0 and 0 for n less than 0. That means whatever multiplication will have, so for negative side sequence, there will be no value, only 0. So the summation will be valid from n equals to 0 to infinite, alpha to the power n. Now let me just remove this un part because we have multiplied n with each of the points of alpha to the power n. Then e to the power minus j omega n. So I can write it like this. Alpha to the power, I can just expand the let me just start writing like this: alpha e to the power minus j omega to the power n, and n equals to 0 to infinite. So it will be just 1 plus alpha e to the power minus j omega alpha squared e to the power minus j omega 2, like that. And this is an infinite GP series again. And as because we have told that alpha is less than 1, so there is no question that alpha into the power minus j omega, it will also be reduced to less than 1. So the summation will be first term divided by 1 minus the common ratio of the infinite series. So the common ratio is how much? Alpha into e to the power minus j omega. So this is the R, or the common ratio. So we get the final result: x e power j omega will be 1 divided by 1 minus alpha e to the power minus j omega. This is the final answer for this particular question. So if you have any questions so far, you can ask regarding the problems that we have solved so far. Okay, I guess there is no question, so let me move forward with the next particular question. So these kind of questions you can observe in any DSP quizzes. So you will be given some particular representation of the input signal xn, and you've been told to find the DTFT at particular instant of time. So we have to find x e power j omega evaluated at omega equals to 0. That means x e power j0. And x e power j0 is what? Xn e to the power minus j0 into n. So that is effectively n from minus infinite to infinite x of n. So we just need to get the value at evaluated at omega equals to 0, DTFT value evaluated at omega equals to 0 effectively reduces to the summation of the signal. So I can write it like, so it will start from -2. So -1, then 0, then 1, then 2, 1, 0, 1, 2, 1, 0, and minus 1. So this is 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 2, that is 6. So the answer is x e power j omega evaluated at omega equals to 0 is summation of xn, n running from minus infinite to infinite, is effectively reduced to 6. That is the summation of this particular sequence. Okay, so this is very easy question. So moving forward to the next question based on the same particular same sequence. So this sequence is given. This is the same sequence apparently, and we have been asked to find what is the value of this particular integral. Okay, so before solving this particular integral, uh, let me just tell you some basics of time domain energy and frequency domain energy. So if a signal xn is basically transformed in the frequency domain, if this is the frequency domain transformation, or DTFT, you can consider e to the power j omega, then energy over here, energy is means what? You take each and every sample of the signal, you take mod, then you take square of that particular thing, and then you sum all the samples over the sample space. So you will, this way you will get the energy of the sample domain signal. Similarly, if we want to calculate the energy of this particular thing, we know that the DTFT is periodic in between minus pi to pi. So we can take one particular period out and we can evaluate this integration x e power j omega. And we are basically concerned about the magnitude part. So I have taken mod square and then d omega. And there is a very well-known relationship called Parseval's theorem. So the main motive of Parseval's theorem is that time domain energy is proportional to frequency domain energy. Same things happens over here, is that summation xn square is proportional to minus pi to pi x e power j omega mod square d omega. And this proportionality constant, when we do the equal sign, so the proportionality constant is this one. So minus pi to pi x e power j omega whole square d omega. That means if we calculate the energy in the time domain, that is related with the frequency domain energy, but just there is a one scaling factor, that is this 1 upon 2 pi. So in this particular question, we have been asked to find 1 upon pi minus pi to pi x e power j omega, then whole square d omega. So we can see that there is a relation. So what is the relation? So I can write it like this: 2 into summation xn whole square, as because we have seen the proportionality constant is 1 upon 2 pi, and here only pi is given. That means 2 will be multiplied at this side. So this particular integration is effectively reduced to the energy evaluated for this particular signal multiplied with 2. So I can write it like this. If I expand the energy summation, so each and every point will take square of the amplitude value. So let me start from here. So it will be 1, then 0, then 1, Then at 1 it is 2, so 2 squared 4, 1 0 1 4 plus 1. Sorry. Yeah. So 1. So at this point this is 4 and this is 1 squared is 1, and then there is a 0 and minus 1 squared is 1. So it will be 2 into so 1 2 8 10. So this is 14. So this will be 28. So this is the particular answer. So given the particular sequence, we were told to find this integral, which is effectively reduced to the uh, uh, twice of the value of the energy of particular sequence given. And if we calculate all these things, so the final result will come to 28, which is option C. Okay. Now we have the same sequence and we have been told to find the angle x e power j omega. So this is a tricky question. Previously we had uh, uh, some relationships. For example, there was a relationship by Parseval's theorem. Otherwise here we just have to do simple summation. Here the thing is that we need to find the uh, phase part of this particular sequence. So let me start solving this thing. So if I sorry, just draw it again. X of n plus 3. Let me just draw x of n plus 3 initially, and then I will ask a question. So this will be 0, then 1, 2, 1, 0, minus 1, 0, 1, 0, minus 1, 1, 2, 3, 4, 5, minus 10, minus 3, minus 5, minus 5. So can you tell me that we had a xn and we did x of n plus 3? What kind of sequence is xn plus 3?
Advanced sequence.
Advanced
Uh,
sequence.
this is advancing operation, but I am asking that can you give some property about this particular sequence, that what kind of symmetricity or what does it contain as far as signals property is being concerned?
Time shifting.
Yeah, time shifting that we had
Symmetrical signal.
done. Yeah. Symmetrical signal. Can you just even more specific? It is symmetrical about uh, this axis. What is the
Symmetrical about y-axis.
uh, what is the exact name of this particular symmetricity property? Okay. You all probably you all know these things, but let me just uh,
It's
write.
a foldable or foldable.
No. Obviously, it will be foldable because it is symmetric about y axis. So the thing is that if we have been given any sequence, let us consider we have yn, and we take yn and y of n minus n. These two things are equal. That means
Even.
yeah. This is even sequence. Yes. Okay. Now we have got some I guess someone is trying to join. Let me see. Okay. We have an even sequence, and the even sequence is x of n plus 3. So I'm renaming it as y of n. So why I'm doing this, there is a particular reason. So in any DSP question, I will request you to use some properties of the signal that is there in the representation. Because if you can track the property of the representation, you'll be able to solve the question in more fast manner. Otherwise, if we start with this particular uh, sequence, you'll not be able to find the solution in a fast way. Otherwise, you'll be stuck in the summation itself. So let me start solving from this particular point, that is x of n plus 3 is equals to 1. So we can take DTFT of this particular thing. So DTFT, we can write it like this. So yn evaluated n equals to minus infinite to infinite. Oh, sorry. This will be DTFT. Yeah. So y e power j omega. Yeah. So this is y of n e to the power minus j omega n. Now I can evaluate it at n equals to 0. Let me just take out the n equals to 0 point out of this summation. So y0 multiplied with e to the power this thing evaluated at n equals to 0. So that means e to the power 0, it will be 1. Okay. So I can write it like this, only y0. Fine. Plus there is summation n equals to minus infinite to infinite. Only n cannot be 0 because n equals to 0 thing we have taken out already. So yn e to the power minus j omega n. And even I can expand it like this, y0 plus n equals to 1 to infinity yn e to the power minus j omega n plus yn e to the power minus j omega n. Now the limit will just be changed. So it will start from -1 to infinite. So at n equals to 0, we have got one component. From n equals to 1 to infinity, we have got second component, and this is the third component, which basically represents summation from -1 to minus infinity. Okay. So let me go to the next page. So y e power j omega, we have got y0 plus summation yn e to the power minus j omega n and yn e to the power minus j omega n. And here the limits are -1 to minus infinity, and this is limit is 1 to infinity. Now we know that for this particular case, let me change the color. Let us consider n is equals to -m. So I can write yn e to the power minus j omega n as it is. This is as it is. N equals to 1 to infinity. This is as it is. But at this point, as I'm considering n is equals to -m, so the limit will be m equals to 1 to infinity. Got it? And then yn is equals to what? Y of -m and e to the power minus, it will become j omega m. Okay. Now we have already seen that yn is equals to minus yn, as because this is a even sequence. That means ym is equals to y minus m. And as because we are just changing the variable, I can change the variable of whole equation like this. So let us consider we now work with single variable yr e to the power minus j omega r, and m also we can change, as because changing the variable will not affect in the particular result. So 1 to infinity y of minus r e to the power plus j omega r. And we just have seen these two are same. So I can write it like this. Whether I have taken extra pages. Why not? And then summation. So I can take yr out, as because these two are same, effectively same. So I can take yr out. So r equals to 1 to infinity e to the power minus j omega r plus e to the power plus j omega r. Now we know that e to the power I theta, e to the power minus I theta plus e to the power I theta divided by 2 is equals to what? Cos theta. That means we have been given these things only. So I can write e to the power minus I theta plus e to the power I theta is equals to 2 into cos theta. So I can write like y of r is varying from 1 to infinity, 2 into cos omega r. That means I can take out this thing 2 into y of r. Oh, sorry. I should keep this yr inside this particular summation. And I should write it like this. And here also, let me just do the same thing. As because summation is on r, so yr also depends on this thing. But inside this part, this is correct, because we have e to the power minus j omega r and e to the power plus j omega r. So we have the trigonometric relationship, and we just have used that particular relationship to get the final answer. So this will be summation 2 into yr and cos omega r equals to 1 to infinity. And this is y e power j omega. So now tell me, ये जो relationship हम लोगों को मिला है, whatever relationship that we have got, is there any imaginary component is there or not? In this particular output, in this particular DTFT, whether we have any imaginary components or not.
No, no
No, there is
imaginary
no
component.
any imaginary
Yes,
component.
so there is no imaginary component. That means this thing is real. And whenever in previous example also, I told that whenever the DTFT is real, that means this is zero phase. So zero phase means there is no imaginary
No
component. So
face.
yeah. So that means these things are very much important as far as question solving is being concerned. So you have to find some way to exploit the relationships. So given the original sequence, this was not a even sequence. So we made the sequence even by advancing it, and then we got the relationship. So previously also I told that if your time domain sequence or the sample is even, then your DTFT will be real. That means zero phase or no imaginary component. That means for this particular thing, y e power j omega, yn is y e power j omega. However, yn is, we have got this thing by advancing the signal x of n plus 3. So Yn has dTft of y power j omega, which has no phase. That means for this particular thing, we'll get no phase, and xn, let us consider this as a dTft of x e power j omega. So x of n plus 3. So what we are doing, we are shifting the signal in the time domain. So we'll get frequency domain shift like this, e to the power j omega 3 x e power j omega. So this is very obvious in basic relationship of continuous time Fourier transform. We know that if we shift the signal in the time domain, there will be an exponent multiplied in the frequency domain with the same frequency content, that is 3 into omega. Okay, now this yn we had written in the time domain that yn is equals to x of n plus 3. So in the frequency domain also this relationship will hold. That means y e power j omega will be dTft of this thing. So e to the power j omega 3 x e power j omega. That means I can write x e power j omega is e to the power minus j omega 3 multiplied with what you call that y e power j omega. And now as far as phase is concerned, because let me go to the question again. We were asked to find the phase of the system. So as far as phase is concerned, this particular thing has got no phase. And this particular thing has a phase of 3 omega. That means it has no phase, 0 phase, and it has a phase of 3 omega, sorry, minus 3 omega. Therefore, the total system, the angle of x e power j omega, it will be minus 3 omega. In this way, you can solve this question. Otherwise, if we were started with this particular thing, the original sequence, and we started to solve the DTFT. So there, obviously, you had to solve the whole DTFT thing. You have to calculate each and every summation, and then you will get a whole sequence of exponents. And then from that whole exponent solution, you need to find the phase. However, using some relationship between the signals. So we just advanced the signal. We got an even sequence, and we know that even sequence has no phase in the DTFT domain. So we can just exploit that particular information, and from there only we can get the final result. Even you don't have to evaluate this part also, because if you know that your sequence is even, your frequency domain will have no phase. You just got to know, and you just evaluate this particular thing, and you will get the answer. So this is just to illustrate you that if you get an even sequence, there will be only real part in the DTFT, and there will be no imaginary part, which will eventually lead to zero phase system. So in this way, we can get the final result as minus 3 omega. So let me just show it over here. So this is the final result. Okay. So moving forward to the next question. The next question is comprises of 3 parts. So xyn is xn 2 into x of n minus n and x of n minus 2. So the first question is determine what is the unit sample response. So let me just draw the basic diagram. So if you have a xn, sorry, let me write it like this. If you have an input and if you have an output, and this is the system transfer function or unit impulse response. So this particular thing we have to find it out. So I can from the output we can see that if we input xn, we are getting some delayed outputs and they are adding with each other. So empirically, I can start like this, and output is hn star input. That means output is convolution of these two. So I have three black box. I don't know what is there inside this whole thing. And then there will be an adder because all these things are added and there are three components. So it is like this. So you have xn and you have yn and you have h1n, h2n and h3n. And we can say if you have been told to find that what is hn. So hn you can write h1n plus h2n plus h3n. Now, when you actually come across these kind of question, again, you need to think of some relationship that has been already covered in the week 1. So at this particular point, if I find the output is how much? H1n convolved with x of n. So at the first output 1 is xn convolved with h of n. However, we got to see the output is xn. So what will be the hn? From the first lecture in the convolution, we have seen that xn convolved with delta n is the original sequence and xn convolved with delta n minus capital N will be how much? Can anyone tell me? If we convolve xn, a sequence with a delayed delta, so what will be the output of the convolution? Okay, so let me just tell you. So this is simple. We are convolving the delta which is located at particular this position at n equals to capital N. So the whole thing will also be delayed by same amount x of n minus capital N. I should write it clearly. So x of n minus capital N. That means output for this particular thing will be x of n. So similarly here I can see that it is delayed by a single unit. So h2 could be 2 into delta n minus 2. Similarly h3 it will be how much? So let me just copy this part over here. This is the output sequence and this is the internal diagram of the system. So let me copy this part over 2. And we just need to find the h1n, h2n and h3n. So from the results, we have guessed that h1n is equals to delta n, h2 is 2 into delta n minus 1 and h3 is delta n minus 2. So now hn I can write it as delta n plus 2 into delta n minus 1 plus delta n minus 2. Now if you have any question like can we get the output with this particular hn, I will show you. Yes, we can get the output. So xn convolved with hn and xn convolved with delta n plus xn convolved with 2 delta n minus 1 and then xn again convolve with delta n minus 2. So this convolution will effectively give you xn. This convolution will give you x of n minus n, and 2 is multiplied over here, and then over here it will be x of n minus 2. So that means this is the uh, whole output. So h of n is finally h of n is finally this particular thing. Now, what is the second question? Is this a stable system? So for stability, we know that stability in the last class also I had solved few questions on stability. Stability uh, is basically defined as if a system is absolutely summable, then the system is stable. Now we need to see the summation h of n, and we have to see whether the summation is basically converging or not. If the summation is converging, then the system is stable. If the summation is not converging, then the system is not stable. So let me just add another page. So this will be h of n, and there will be summation over all n, and I can draw the hn. So this is at n equals to 0, at n equals to 1, this is has 2, this is 1, at n equals to 2, again this is 1. So if I do the summation, so the summation will be for this particular thing from minus infinite to infinite, this will be reduced to 0 to 2 h of n. So effectively 1 plus 2 plus 1, therefore 4. That means this is less than infinity. That means it is converging, and this is a stable system. Stable system and absolutely summable. So this is a stable system. Okay. And we have to find the DTFT. So h e power j omega. So DTFT of delta n, then DTFT of delta n minus 1 and 2 we can take out obviously, and DTFT of delta n minus 2. So we can just have to find the DTFT of delta n. Rest of the things we can find by using property. So let us just find the DTFT of delta n. So we can write delta n e to the power minus j omega n, and n is running from minus infinite to infinite. And we can see that delta n is multiplied with this particular sequence. So we can write delta n e to the power minus j omega evaluated at that particular location where delta exists. Now delta n exists at n equals to 0. Therefore, this will be evaluated at n equals to 0. So we can write summation of delta n, and we all know that delta exists over at point 0. So if we do summation over from minus infinite to infinite, the output will be 1. That means h e power j omega will be 1 plus 2 into, now we have a shifting in time. Therefore, we'll get some multiplying factor e to the power j omega into 1, and then e to the power minus j omega into 2. Got it? So the final result is 1 plus 2 into minus j omega and e to the power minus j omega into 2. So even in the question, I guess they have told to reduce it using trigonometric identities. So I can take 2 into e to the power 2 into e to the power minus j omega. Yeah, let me just take 2 into the power minus j omega. So it will be half into e to the power j omega, then 1, then this will be how much? Half into e to the power j omega minus j omega. So let me take one page extra. So let me just copy this whole part so that it continues. So this is basically what you have over here is 2 into e to the power minus j omega followed by these two things. If we club together, we'll get cos of omega and then plus 1. So h e power j omega is basically this is the final result. OK. So moving to the next question. Next question, we have told to find the DTFT of output when input is a delta function. So let me just write the output. What is the output? Yn is the output, and we can write Yn as Wn. Wn is coming over here. So this is Wn, and there is some multiplication is going over here. 1 minus 1 to the power n and Wn. So this is the output sequence. But we need to find the DTFT when xn is basically delta n. So let us consider that this particular guy has inverse DTFT of hn, then Wn is what? Hn convolve with xn. Now hn convolve with delta n. And we already have seen that hn delta n, if it is converted with any particular signal, it will get back the original signal itself. So Wn is what? H of hn. So I can write that yn in terms of the hn. So hn plus minus 1 to the power n hn. Now I need to find the DTFT. So y e power j omega is equals to h e power j omega plus minus 1 to the power n h e power j omega. So y e power j omega h e power j omega. So can you tell me that what can I write this particular thing? There is a very this is a very basic representation of any complex exponent. Can you just tell me what can I do this particular thing? So let me just show you. Minus 1. We know e to the power minus I theta is cos theta minus j sin theta. And if theta is pi, then e to the power minus I pi is equals to cos pi minus j sin pi. Now j sin pi is what? 0 and cos pi is 1 minus 1. That means minus 1 to the power 1 to the power n. We can write it as e to the power minus I n theta. Or as because we are dealing with omega, let me just change the variable to omega. So this is a note. So I can write it as minus I j omega n h into e to the power j omega. So I can take this is I'm just reducing this 1 plus e to the power minus j omega. So this is the final result. I guess we are left with this question. Okay. So in this particular question, we have been told that this is a signal, input signal, and we are passing it as it is. And we are passing, the second component is passing through some particular transfer function or unit impulse response, and whose DTFT is defined like this, and we are getting output yn. And we have a sequence wn, which is xn plus j omega n. That means we are doing this kind of operation. So I guess someone's trying to join. But what is the point? Okay, so j is multiplied with this, and then we are taking summation over here. So we are getting wn. So that is why wn is written as xn plus jyn. And this has a particular representation h of e power j omega from 0 to pi. This is 0 to pi. This is minus j. That means this, and from this side to this side, it is plus j. Can anyone tell me that what kind of signal is this?
Is it a sigmoid signal?
This is signum.
Signum function.
Signum. This is signum function. Yes, yes, yes. This is signum function. Yeah, right. But there is a catch. Signum function generally looks like this. This is the original signum function. And here we can just see the reverse operation is there. So I can take minus signum of omega. So this is the particular thing is like this, h e power j omega. I can write it as minus signum of omega. And we have been given that the magnitude part xn has a magnitude like this, and it has imaginary component 0. So from here again, we can get some information that your xn, the DTFT of xn has no imaginary component. It has got only real component. That means it's a zero phase system. And we can even talk about the time domain representation also. This is a even signal in the time domain, as because it has got zero phase system in the frequency domain. So in this way, you always have to actually infer the relationships. And the question is that we need to sketch w e power j omega. So w e power j omega is basically, and so wn is basically xn plus j into yn. So x e power j omega plus j into y e power j omega. Now in the previous section, we have seen that yn is passed through this particular uh, block. So I can write yn as hn convolved with xn. So y e power j omega, it will be h e power j omega multiplied with x e power j omega. Got it? Now x e power j omega, they have given all the diagrams. So this is how x e power j omega looks like. This is x e power j omega. This is omega r. This is minus omega r. This is pi. This is minus pi. And we have seen that h e power j omega looks like this has minus j, and this is plus j. Now I am multiplying h e power j omega with x e power j omega. That means if I do multiplication of these two, so y e power j omega, it will look like, let me just change the color. it will look like. So this part is multiplied with minus j. That means this thing will get minus value and have a this is 1. So have a highest peak at minus j. And this part will be as it is because we are multiplying j only. So this will be minus omega r, this will be omega r, and this is at j. So this is y e power j omega. Now to draw the DTFT of this thing, magnitude spectrum of this thing, we have got already this sketch of x e power j omega. But we have to multiply the y e power j omega with j. So let me draw this part again. So j into y e power j omega. So j into j, it will be what? -1. So everything will come like this. And this will be j into j. It will be -1 and there is minus already. So this will be shifted to the plus side. So omega r minus omega r omega. So this part is j into y power j omega. And similarly, we have let me just change the color. So this is j into y e power j omega. Let me draw this thing also. Omega r minus omega r, and this is +1 and this is -1. However, this is 1. Now we need to add these two to get w e power j omega. So if we add these two things, we will get these two part will cancel each other because this is just the opposite, and these two part will add up. Therefore, the highest peak will be at 2, and this is w e power j omega, and this is omega. So in this way, we can find the output sketch of w e power j omega, which is basically represented by x e power j omega and j into y e power j omega. So we have been given the sketches of individual functions, and then we can figure it out how to find the uh, output output DTFT magnitude spectrum. So with this, the question session basically ends. So if you have any question regarding the questions that we have discussed so far, you can ask me. And I will share all these slides with you. So I guess NPTEL team. So let me have a discussion with you. So I guess NPTEL team, they basically sends the YouTube link of the lecture as well as the slides, unannotated and annotated, to you through mail like this. Is it so?
Sir, for the
No, sir.
previous
Yes, sir,
year,
we
we
need.
didn't receive any slides for the online session.
Okay.
Till now, we are not still on slide.
Okay. But have you got the YouTube link of the last
Yes,
class?
yes.
So one
YouTube
link
link
you
for
have shared when I requested you through the discussion forum.
Yes. But NPTEL team, whether they have shared or not.
Not yet.
No, sir, we didn't get any YouTube link for the first session, sir. We need that one also.
Okay. So
Please provide that.
you yes, I will provide. So you can search my name in YouTube. My name is Arka Roy, and you'll get my channel, and I am uploading all the videos in the same playlist. So from there you can actually get the uh, YouTube video links. So let me just see. I guess I have the link somewhere. Uh, Probably in the discussion forum or something I had mailed once. Uh, Yeah. So I'm just pasting the link over here in the chat box. Okay, so you can get the. So you can get the video link from here. And regarding the what do you call the slides that I will put in the NPTEL that discussion forum itself. So let me just have a discussion with the NPTEL team and I will share you shortly. So I have uploaded already the week 1 and week 0 questions. Uh, those are not the live questions because discussing the live questions that is wrong because till now you have not been graded and the due date of the week 1 question is I guess 9th of August. So after 9th of August, if you have any questions regarding the quiz also for which we have been graded, I can discuss those questions too. And there will be another TA who will be taking this session on Sunday, I guess. Uh, uh, is it so?
Sir,
There
will
is
the
another
Sunday
TA.
session will cover the same topic?
Uh, I guess he will be covering some more questions on week 2 content or week 1 content. So he will be covering more questions. So here our main aim is to solve enough questions so that it will be beneficial for you to solve the questions that is there in the quiz. So I guess these questions that we have discussed so far will be helpful. It will be helpful for you to solve the quiz questions. So that is the main motto. So the other TA, he will also be solving more questions on week 1, week 0, and week 2 contents. So do you have any further queries?
No, sir. Thank you. Thank you, sir. Nice
Okay,
session.
okay, okay. Thank you all. So let me stop the recording.
Thank you, sir.